So the joint PMF is really pretty simple, and to make sure you understand it, take this quiz. We'll start with the quiz solution in part 3 of this lecture. Okay, so we're starting part 3 of lecture 16, and we're continuing our study of the joint PMF of a pair of random variables. And so let's take the quiz. Quiz is actually really simple. If we start with a pair of random variables Q and G, whose joint PMF is given in the table shown here. So the first question is, what is the probability Q equals 0? And for the probability Q equals 0, we just look at all the possible values of Q and G that have non-zero probability where Q is 0. So for instance, we can have Q is 0 and G is 0, Q is 0 and G is 1, Q is 0, G is 2, Q is 0, G is 3, and to calculate that probability, we just add them up. This is the probability of Q and G of 0 and 0, plus the probability of Q and G 0 and 1, plus the probability of Q and G 0 and 2, plus the probability of Q and G 0 and 3. And now I add those up and I get 0.06 plus 0.18 plus 0.24 plus 0.12, and the answer is 0.6. In part B, we're asked what's the probability Q equals G, and for Q equals G, we just look and say, well, one possibility is Q is 0 and G is 0, and the other place where Q equals G is Q is 1, G equals 1. And we could write out what terms of the PMF we're adding, but you could just say, well, it's 0.06 plus 0.12, it's 0.18. Part C, we're asked what is the probability G is strictly greater than 1? And that means G is 2 or G is 3. And we look at all the QG pairs where G is greater than 1. And we have these 4 pairs. And then we add up their probabilities. I think I'll use a different color pen. Thank you. 0.24 plus 0.12 plus 0.16 plus 0.08, 0.36, 0.46, 0.52, that's also 0.6. Finally, in part D, we're asked what's the probability G is greater than Q? And that event includes the following pairs. It's for Q equals 0, it's all the G's greater than 0, these 3 pairs. And for G equals 1, for Q equals 1, it's G equals 2 and G equals 3. And if you add up all of those probabilities, you get 0.18 plus 0.24 plus 0.12 plus 0.16 plus 0.08. And that adds up to 0.78. What this quiz demonstrates is that once somebody hands you a joint PMF, particularly in a table form, whatever probabilities you want to calculate related to the variables in the table, it's just bookkeeping, finding the pairs that meet the condition and adding those probabilities up. So now we're pretty comfortable with the joint PMF of x and y. And sometimes you have an experiment that generates a pair xy, but maybe you're just interested in calculating probabilities with respect to x, and what you want is just the PMF of x. Or maybe you just want the PMF of y, And somehow, if the joint PMF is a complete probability model for all XY pairs, then we should be able to deduce these PMFs of the individual random variables X and Y. In probability speak, these individual PMFs are called marginal PMFs. And finding marginal PMFs is the topic of this section. Turns out that finding marginal PMFs is actually pretty simple, and it's summarized in this theorem. So to find the marginal PMF of X, you sum the joint PMF over all possible values of Y. To find the marginal PMF of Y, you sum the joint PMF over all possible values of X. And this is really just an outgrowth of our earlier theorem for finding the probabilities of arbitrary events. So for instance, we let random event B be that random variable X is equal to little x. So in this case, the PMF at little x is the probability X equals X, which is equal to the probability of B. And we had our earlier theorem about how to find the probability of B. You just summed over all x's and y's belonging to this set B. You sum the PMF. But in fact, x and y belongs to B is exactly the set. It's if and only if x equals x. So what you're doing is you sum over all x, y pairs such that x equals x, right? What that means is you sum over all values of y. To be frank, I think I've kind of been a little bit laborious here and made something that's really simple seem a little bit more complicated. In fact, it really is simple. To see how simple it is, let's go back to our example from the two circuits where we found a joint PMF in table form for x and y. So now we'll find the marginal PMFs for x and for y. So here we've duplicated the table of the joint PMF because it makes doing our calculations a little simpler. So the theorem says that the PMF of x is equal to the sum over all y of the joint PMF. So for example, what you do is you think about setting a particular value like x equals 0, and you sum over all y, the joint PMF at x equals 0 and all y. And the thing to see here is that this sum is exactly equal to the row sum for the row x equals 0. So in fact, what we can do is that we can write a column on the end here, px of x, right? And for x equals 0, we sum the first row, 0.01. For x equals 1, we sum the second row, so we get 0.18. And now we sum for x equals 2, we sum the third row, and we get 0.81. And in fact, this column over here on the right is the marginal PMF of x. If we go back to our old notation, we would write something like Px of x is equal to 0.01 at x equals 0, 0.18 at x equals 1, 0.81 at x equals 2. And then if we're being careful, we'll put in a 0 otherwise, just to be completely clear. So the second half of our previous theorem said that we can find the PMF of y as equal to the sum over all x of the joint PMF of x and y. And in the same way as the previous sum was a sum over all the rows, this sum is for a given y equal to a sum over the columns. So for example, py of 1 is equal to the sum over all x of p of xy of x and y equals 1. And this sum here is precisely this column sum for y equals 1. So we see that, in fact, the PMF of y is found by column sums. So what we do here is we draw a line at the bottom of this table, and we label py of y, and we do the column sums. So for the column sum for y equals 0, 0.1. The column sum for y equals 1 is 0.09. And the column sum for y equals 2 is 0.81. And these are the entries for the PMF of y. Specifically, the PMF of y is equal to 0.10, y equals 0, 0.09, y equals 1, 0.81, y equals 2, and 0 otherwise. So these PMFs are called marginal PMFs, and when I first learned about this, I thought they were called marginal in the sense that they have a kind of a partial or an incomplete description of the random variables x and y. After I taught this course a few times, I found out from my co-author that in fact the name marginal comes from a different reason. If you have a really big table and the table fills up your page, then you write this column over here on the far right for the PMF of x, and you write it in the margin of the paper. And in the margin of the paper, you do your row sums, and this is your marginal PMF because, in fact, it's in the margin of your paper, not because it's marginally useful or anything like that. So the next two slides have exactly the same solution as it's worked out in the book, and we'll leave them in the slide deck, but we'll skip over them and jump to the next topic. This quiz is so simple, we might as well just do it here. So we'll label on the right side, we'll label the marginal PMF of H, and we'll do the row sums, 0.6, 0.2, 0.2. And down here at the bottom, we will label PB of B, and we'll do the column sums at B equals 0, 0.2, 0.5, 0.3, and if you want to be completely precise, we write out these PMFs explicitly. 0.6 at h equals -1, 0.2 at h equals 0, 0.2 at h equals 1, 0 otherwise, and PB of B equal to 0.2, B equals 0, 0.5, B equals 2, and 0.3 at B equals 4.